All right, so I want to go back and look at this example. And we have our parabola and we have our 2 points, input and output. And so I am going to go over to my dot cam. So this is it, not so pretty. And I might want to find the rate of change, which would be if I drew a line between those 2 points. And again, it's not going to fall on this because this is constantly changing in here, constantly changing. But I could draw a line through those. It would only go through those 2 points. What's the slope of that? Rate of change is just slope. When I was in calc, this drove me nuts. I'm like, what's going on? But this is your output when you sub in B. This is your output. So really it's just saying, what's your output? What's your output? Those are your Y's. So in high school, you probably did Y2 minus Y1. And then what's your input and input? And so Y2 minus Y1. So in high school, you might have gone, 9 minus 4 over 3 minus 2, order matters, 5 over 1, the slope is 5. That's your rate of change. I kind of like to make an input-output chart. So the input to my function is 2, 2 squared is 4, that's my output. Input to my function is 3, the output is 9. All right. And I like to do change in Y over change in X. So how's my Y changing? It's going up by 5, up by 1. So positive 5 over positive 1. My rate of change is 5, which is your slope. Now, what we like to do then is we like to move that down. So what happens if I get really close? So say I sub in 2.1 into my function. All right, so that's a decimal there. And again, on my app, I download the Desmos app here, and that's a free download. So 2.1, oopsie, helps if you type it in right. 2.1 squared is 4.41. So 2.1 and 4.41. And I want to find the rate of change between these guys because now this is going to be a different line if I drew it, okay? So I'm going to ditch this point right here, and I'm not going to do this. I'm going to do it the way I like. So I am going to say, okay, that guy went up by 0.41, 41 hundredths went up. This went up by 0.1 or 1/10. And so if I divide those, and again, kind of an easy way to do that is just multiplying both by 10 and get 4.1 over 1. So I know my rate of change is 4.1. So when I was doing this distance between those 2 points, it was 5, but as I narrow in, my slope or my rate of change is 4.1. So if I get out of here, let me go back to Desmos. So if I type in that other point, so our input was what, 4.1, is that right? Or no, 2.1, sorry. So we had 2.1, helps if you can type 2.1. And then our output was what, 4.41, which again would be the area if you made a square. All right. So, and I can label that guy. So as if this point were to slide down and I made a line just between these two, that rate of change or slope would be 4.1. Okay. Some other things we can talk about this function is increasing and decreasing. And let me just take a screenshot here quick. Oh, never mind. Let me get out of that. Here, let me do a screenshot. So we can write on this guy. You could do it. All right. So if we talk about, well, we could do domain and range. Okay, domain as I go across, right? If you look as I go across, domain would go from this way. So negative infinity to positive infinity, or you could say all reals, just kind of depends on the situation, what your teacher wants, what my math lab wants, or Newton, I don't care. Range is the one time we're focusing on Y values, okay? So this guy down here is at 0, 0. So remember, you ignore the X on this guy, and we're just focusing on the Y values. So 0 included off to infinity. So those are domain and range. All right, what else could we focus on? We could focus on increasing and decreasing. All right, so if we think of a little kind of a cart going down, right? So on a roller coaster, this guy is decreasing from negative values on X. And again, this is all focused on X. We're not, range is the only time we focus on Y. So negative infinity, and then it stops. And again, think about this as 0, 0. We only care about the x's here. So it's going to stop at 0. Again, I use parentheses. I don't know what your program does. You'll have to figure that out. And it varies. So in Calc, it could be different. So just make sure you know. I don't care. All right. And then do you see how it's increasing at this point? Maybe if it lets me, right? So starting at that 0, it's going to increase and go off to infinity. So at that 0, goes off to infinity. All right. And the reason is because as these x's come out here, right, there's always going to be a y value up there. All right. The other thing we could talk about here is also x and y intercepts. We could also talk about local mins, local max. And so I'll try to talk about those too. So we can do it in this context, and then I'll try to do another one. So in this case, the x-intercept and the y-intercept are the same here. So we have 0, 0. That's both the x and the y-intercept because it crosses them both. And that's the only place it crosses. So that is your x and y-intercept. All right. The other thing we can talk about is a local min and a local max. And I'll do more of this in a second. But this is a local min value because it's the minimum value in that middle area, kind of in the middle of town, so to speak. So that's a local min. It's also the absolute min because this function never gets lower than that. This function does not have a local max. There's no, this is going off to infinity, right? So there's no local max and there's no absolute max. Okay. Now I'm going to talk about locals. Locals technically have to be in the middle somewhere. So they can't go off to infinity anyway. So I'm going to switch gears. I'm going to pause this just for a second, and then I'm going to give you a graph to help talk about that. All right. I've had a few issues to say the least. Okay. Local mins and maxes have to be in the middle. Absolutes can be anywhere. And there are some weird things every once in a while. So these three are local mins, because in their neighborhood, that's the smallest in that area. This is the smallest in that area. That's the smallest in the area. And how you write them, again, kind of depends on. Sometimes we could say there is a local min of 0, right? That's my y value. So the lowest value of the function is 0. And then that would be at what? X equals a -1. Or maybe at x equals 0, and the other one at x equals what, 2? Sometimes they might write these as ordered pairs, so local min at -1, 0, 0, 0, -2, 0. So it just depends on your textbook and the question. Now, in this area, this is a max, and this is a max, but just in that little neighborhood. So again, I would say there's a local, I guess I'm writing in this here, a local max. What's my maximum value there? What does that look like? This is like 0.1, 0.2, 0.3, 0.4. No, they're going by 0.2s. So it looks like there's a maximum of what, 0.4. So a local max value of 0.4 at when x is a negative, what is that? Negative, maybe, that doesn't look like a -1/2, maybe -0.6. And then this one looks like what? 4 point, maybe 4.1, if I had to guess, maybe, when x is about what? 1.2, something like that. Now, as far as an absolute minimum, these values down here are the absolute min. 0 is the absolute min this graph ever gets. It never gets more smaller than that for output. But as far as an absolute max, do you see how this guy goes off to infinity? So there is no absolute max. So there's local mins right here. There's local maxes right there. These are the local maxes. Absolute mins, yep, doesn't get smaller than these. So these 3 points are all absolute mins. So you have an absolute min value of 0 at these 3 points. But as far as an absolute max, not so much because it goes off to infinity. All right, I'm going to just sketch one so you can kind of see maybe what some of the weird ones look like. All right, let's look at this graph. Again, there's infinite many points here, right? So I'm just kind of emphasizing certain ones. But as far as locals, they have to be in the middle of the problem. So this guy cannot be a local. The ends can never be local, okay? So what do I have here? Well, there's a local max, okay? And the maximum value it gets is a y value of 2 when x is 1. So local max of 2 at what? X equals 1. So the maximum in that area is 2. Here in this neighborhood, we have a local min. Okay, what's the minimum value there? 0 at what? X equals a positive 2. Okay, now that is it for locals because these are the only kind of high or low points in the middle. All right, now we can look at the whole graph to do absolutes. Okay, so let's see. And if this is not an absolute min, it still can't be a local. So locals can never be at the ends there. So this guy is lower than that. So this is an absolute min of what? -1 at x equals -2. Okay, so there's an absolute minimum value of a -1 when x is at a -2. Okay, now absolute max, well, we have this guy, but see, this is going off to infinity, right? And getting higher, higher, higher. So absolute max, there is none. Okay, all right. I'm gonna pause it again and try to draw a graph of some other weird situations. Okay, say you have a situation with like this, which again, we have some holes here, so that is a problem. All right, so in the middle, I'm gonna kind of circle the middle right there. That is where you can find locals. Okay, this is a hole. It cannot be a local min, max, can't be an absolute min or max. And the reason is, excuse me, is you can't land there. And if you're like, well, why can't you say, you know, you're really close to a minimum value of a -1, but it, you know, maybe it's a -0.9999999, and I can keep getting close to it. So that's a no-go. Holes are a problem. All right, in this neighborhood, there is a max. So 1, 2, so there's a maximum value of 2 at what? X equals 1. This guy right here, what is that? 1, 2, 3, 1, 2, 3. So 3, -3 is the point. So that is a local min of, so local min of a -3 at x equals 3. Over here, again, in the neighborhood, so 1, 2, 3, 4, 5, 6, 3. So again, a local max of 3 at x equals 6. This is a local min in that neighborhood, 1, 2, 3, 4, 5, 6, 7, 8. So this ordered pair is 8, 1. So there is a local min of 1 at x equals 8. Over here, what was that? 8, 9, 10, 11. What's point 1, 2, 3, 4, 5, 11, 5. So again, local max value of 5 at x equals 11. And then that's the only thing. So again, cover up your ends. They cannot be a local. Even if this was a solid, let's put a solid point here. He cannot be a local, even if he's a solid point. Okay, anything is open for absolutes. Okay, now this guy cannot be an absolute no matter what because he's a hole, and you can always get infinite many closer. So, and is it higher? Are those on the level? Yeah, they are. So I could say that there's an absolute max of 5 when x is at 11. I could say that. This guy can be an absolute min. That is allowed. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then what? -1, 2, 3, 4, 5. I could say there's an absolute min of a -5 when x equals 13. Okay. And again, this guy cannot give me the absolute max because he's a hole. This one is the absolute max because this one might get really close to 4.9999999, but this one actually lands at 5. So that one can be. All right, it can get confusing, but you can do it. Take care.